Swayam Prabha. Digital India. Educated India.
So, hello everyone. So, we will continue with the different terminologies used in tensile testing. So, the specific stress or mass stress, it's the basically ratio of the load per unit linear density. So, in case of textile material, the linear density is used instead of cross sectional area, that as we have already discussed. So, it also allows the strains of yarn of different linear densities to be compared. That means, suppose we have two yarns, one is 10 ticks, another is 20 ticks, okay, and the 10 ticks yarn is having strength of 100 centinewton and 20 ticks yarn is having breaking strength of 100, say 40 centinewton. So, if you compare the strength of the yarn, so this is yarn 1 and yarn 2. So, yarn 1 will be weaker than yarn 2, but this lower strength, lower load, breaking load is mainly due to the finer yarn count, finer text. So, to compare these two yarn, the strength of these two yarn, if we take the mass strength or specific strength, that is breaking load 100 by 10, it becomes 10 centinewton per text, and whereas the yarn 2 will become the breaking stress or specific stress will become 140 divided by 20, that is 7 centinewton per text. So, although yarn 2 is having higher breaking load, but the stress of this yarn, breaking stress or tenacity of the yarn is lower than the tenacity of yarn 1. So, we can compare these two yarn in terms of specific stress. It will be wrong to compare the breaking load between two yarns with different linear density. So, tenacity, as we have already discussed, it could be specific stress at break, it will be specific stress at break, it will be in that particular case where the material breaks at this maximum load, and otherwise it is typically specific stress at its maximum force point. So, we can see here the green color, here it breaks at its maximum point. So specific stress at break can be used, but yarn with green, blue color, here the tenacity will be taken as the maximum point. Now breaking length is a concept. This is typically, it's not practically used, but it's a concept. What is the concept here? Suppose, imagine we have a yarn cone of yarn and we are endless yarn. So there are large quantity of yarn and we are, someone is taking the yarn okay up. So it's taking up the yarn continuously, and there will be certain height after he is continuously moving up. So after reaching certain height, okay, h, it may be few kilometers. After reaching that height, the yarn will have certain load. That load will break the yarn. If we consider the stress strain load elongation behavior, this is the load elongation behavior. Here the load is say L. At L load it breaks. At L load it breaks. So after reaching H height, it has been observed that the mass of the yarn of that height becomes equivalent to L. Total mass is equivalent to L. That means this height, at that height, the yarn will break at its own mass. So this height is known as the breaking, or this length is known as the breaking length. Okay. It is the theoretical length in kilometer. So breaking length is expressed generally in terms of kilometer. So it is the theoretical length of a specimen of yarn whose weight without exerting a force is sufficient to break the specimen. That is the theoretical concept, and it is used mainly for yarn. For example, say we take the 10 tex yarn and that breaks at load of 150 gram force. So 10 tex yarn, you can see breaking length will be 15 kilometer. So how is it coming? So for 10 tex yarn, if we have 150 gram, so 10 gram, so 10 tex, as per the definition, 10 tex means length, here length is 1000 meter, or say 1 kilometer, yarn weighs 10 gram. Okay, 10 gram. So 10 gram yarn of length 1 kilometer. 150 gram yarn will have say 15 kilometer. 150 gram is the breaking load. So 15 kilometer. So 15 kilometer is the breaking length, and breaking length is expressed in terms of RKM. So breaking length is expressed in kilometer always. So R is the term R comes from the breaking and kilometer in length. So breaking length in kilometer, RKM. So breaking length is 15 kilometer, and if we measure the gram per tex value, so gram force per tex, so gram force is breaking load is 150 gram force per tex 10. So tenacity, this is the tenacity of yarn, it's again 50. So breaking length and tenacity, numerically the values are same. So that's why in the yarn specification we will see the strength specification, we see the RKM value. We hear the term RKM. RKM means the breaking length, but we don't measure the breaking length, we measure the tenacity in terms of gram per tex, and we simply call it as this is the RKM value. Okay, so they are the same numerical value in gram per tex. So stress strain, so strain or elongation, strain is nothing but elongation by initial length, not the extended length. And extension percentage or elongation percent, when we express the strain in terms of percent, we call it as extension or elongation percent. And gauge length, I have already mentioned the original length of the portion of specimen under test between the jaws. That is the original length. It's not the length after load. Now we will discuss the analysis of stress strain curve. Now we can see the animation here. So a stress strain curve is being drawn the way I have already explained. Now one tangent is drawn on the initial portion of the stress strain curve from the origin and the angle here theta and tan theta is known as the initial modulus within the hook region. Tan theta is the slope of the initial point, and A dash and A double dash, it's very small portion. The measurement may be difficult, so we can extend this line to B point. From there we can measure, it's measurable distance. And the say OA or OA dash, it's a very small, within say few millimeter. Okay, and the point which we can get point C. The point C here is the yield point, and from the yield point we can also measure the yield stress and yield strain. Yield stress is C double dash, that is the OC double dash, this height, this point. OC double dash is the yield stress and OC dash is the yield strain. And at the breaking point, that is E, from there we can get OE double dash, which is breaking stress or tenacity, and OE is the breaking strain. Apart from this, we can also calculate some other modulus. So modulus at any point we can calculate. Say D is any point in the curve. On the curve, any point. So, and if we join with the origin O, and OD is making certain angle with the x-axis. So from there we can calculate the secant modulus also. The secant modulus is the slope of the straight line drawn between 0, the origin point, and any specific point. So this secant modulus is important to know the modulus at any specific point. Suppose we want to measure the secant modulus at certain stress or certain strain, so we should be able to measure. So this is the curve which we have discussed in the animation. So initial modulus is, or we can call it as Young's modulus. So within the Hooke's region, where stress strain behavior is following straight line relationship. So the slope is, we have discussed, A dash by A double dash, or B dash B double dash, because B we have just extrapolated this line, and secant modulus is slope of the straight line drawn between 0 and the at any specific point D with known strain or stress. Suppose we want to measure the secant modulus of strain OX. this is the strain X point. So we simply identify this point, say D, and we join O D and get the value phi angle. So tan phi is the secant modulus. So secant modulus can be obtained for a specific stress or any specific strain. Another important term which is tangent modulus. It is defined as the slope of a line tangent to the stress strain curve at a particular point. So secant modulus we have seen at any point when we join that point D with the origin. Okay, and that if we measure the modulus at that point, so tan phi is the secant modulus. But at this point, if we want, at the point D, if we want the tangent modulus, we have to draw a tangent at this point only of the curve. So tangent of the curve, and then we can get the slope. Okay, slope of this point at this point. So tan alpha is the tangent modulus at point D. So tangent modulus can be drawn, can be calculated at any point of time. Okay, and which will represent the slope at this point, at particular point. Now if it is asked tangent modulus within the Hooke's region, so tangent modulus within Hooke's region, if we try to take, this is the Hookean region, so it will be equal to the initial modulus. Tangent modulus always changes. It remains constant, equal to initial modulus up to the Hooke's region. Then depending on the curve, nature of curve, it always changes. Sometimes it becomes lower and then it becomes higher depending on the nature of curve. So it gives it's very important for any material, any engineering material, also in case of textile material. For engineering material, it's very, very important where high load is being applied. Now let us see a material which will be subject to a certain strain during its application. Suppose this strain is at this point, at up to that strain it will subject. So at that point, initial modulus or Young's modulus is not going to help. At that point, how the load elongation, how the stress strain behavior will take place, how it will be actually to resist, that will depend on the modulus at that point, the tangent of it, whether there will be greater extension after that or not, that's important. In textile material, we normally, for apparel purpose at least, we normally deal with within the Hooke's region. But for technical textiles, we may reach beyond the Hooke's region. So there the tangent modulus is important. Okay. Now let us see what is happening within this. Why the nature of curves are different. It's behaving like this. So OA, its elongation due to stretching of primary and secondary bond within the fiber. So if you have a fiber, so these are the molecules. So I will draw in the different color. These are the fiber molecules. So there will be some bonds, okay, between the molecules. While applying load, this primary and secondary bonds will get straightened, stretched, and then if we relax, if we release the load, they will come back. So which will be totally recoverable, and that's called elastic zone. Okay, OA here is only due to the stretching of primary and secondary. And when we cross the point C, the curve bends sharply towards the elongation axis or strain axis. So where larger strain at smaller load. It is with a small increase in load, the larger strain takes place. This is known as yield point. And this yield point occurs due to the breakage of some primary and secondary bonds. Here, primary and secondary bonds are breaking. So due to the breakage, they are in a position to get much more consolidated. So O C dash is a yield strain and OC double dash is yield stress. Now, after this, a plastic flow occurs. So there will be movement between the molecules. Okay, and breaking of some secondary bonds will take place, and molecular sliding takes place, so that there will be easy extension, and rearrangement of molecules will take place. This rearrangement puts the material in a better position to withstand further load. So it has been straightened, molecules have been straightened. So they are now putting a load. So with the smaller, that is the load, with the increase in load, the strain will be lower. So the nature of curve varies depending on the molecular structure of fiber or yarn structure. So yarn structure also, if we change the yarn structure, so nature of curve can be varied. The nature of curve depends on the molecular structure of fiber or yarn structure. You can see here, flax has got very high modulus, whereas wool has got very low modulus. This is mainly due to the molecular structure. Cotton and polyester are interrelated. And also, if we change the molecular structure like low oriented yarn, partially oriented yarn and fully drawn yarn, for same fiber, say polyester, we can change the stress strain curve by rearranging the molecule structure. We can also change the molecular stress strain curve by chemical treatment. The stress strain behavior with high chemical concentration, the molecular degradation takes place. So, the breaking load or elongation decreases. By changing the twist multiplier, we can change the stress strain behavior. Is a TM1, TM2, TM3. So, lower twist multiplier, moderate and higher twist multiplier. As we increase the twist multiplier, the breaking load initially increases, and when it crosses certain limit, then it further reduces. And similarly, the modulus also gets changed.
Okay, so our next parameter is work of rupture. So, what is work of rupture? Work of rupture is nothing but the toughness of material. That means, when we apply stress in a material, the material gets extended. Like if we see a load elongation behavior, this is in y axis we have load and in x axis it is elongation. So, the typical load elongation behavior of textile material is like this. So, during this path, elongation path, the energy required is the area under the load elongation curve. So, this is actually it is a work of rupture. Now, this work of rupture is the energy or work required to break a material. It is a up to the, if we take up to the breaking point, that means it is a work of rupture up to breaking point, and we can take at any other specified elongation point. So, that is expressed in terms of the multiplication of say load unit and elongation unit. So, that is the work done. So, if the load unit is say centinewton and elongation is say centimeter. So, work of rupture W will be equal to centinewton multiplied by centimeter. So, this is the unit. And the curve is like this. So, if we have a known function, if we know the function of this load elongation behavior, so in that case we can get the work of rupture by integrating within the say starting point 0 and at the rupture point. So, that way we can also measure the work of rupture. So, as I told that unit is the unit of the work of rupture is the force unit multiplied by the elongation unit. Now, here the thing is that this work of rupture of a material is a function of the load. So, sorry, the function of the gauge length. Okay. Now, you can see here two materials. If I show the curve, one yarn, say yarn, one yarn, the gauge length is say 10 centimeter. So, this is the load and this is x axis is elongation. So, with the 10 centimeter gauge length, the load elongation behavior is this. So, it is elongating and here is the breaking load. So, it breaks at this point. Here you can see here that this work of rupture of this yarn with 10 centimeter gauge length is say W1. Now, the same yarn, if we take a gauge length of say 20 centimeter and considering that or neglecting the impact of gauge length on the breaking load, this is the breaking load. In that case, the breaking load considering for both these gauge lengths are same. So, in that case for 20 centimeter gauge length, the load elongation behavior will be like this, the green dotted line. So, here as the gauge length is more, so elongation will also be more. So, we can see for 20 centimeter gauge length, the area under the curve is more than that of with 10 centimeter gauge length. So, we can see, so this is W2. So, same material we are getting two different values of work of rupture. So, it is a little bit misleading. So, in another case, let us consider another situation where we have a same material with different linear density. So, different texts. So, this is elongation and here in x axis is load. Now, yarn 1 is of say 10 texts and yarn 2 of say 30 texts. So, yarn 1 is definitely finer than yarn 2. So, yarn 1 will have lower breaking load and yarn 2 as it is thicker. So, it is a coarser yarn. So, yarn 2 will have, so this is yarn 2 will have much higher breaking load, although they are made of same fiber say cotton and there is no way to compare the work of rupture. So, yarn 2 which is thicker one will definitely have higher breaking load. So, it will give the higher work of rupture. So, can we compare the work of rupture between 10 texts and 30 texts? So, we have two different parameters, one is gauge length, another is linear density text say Tx of the yarn. So, in these cases So, if we want to compare the yarns tested at different gauge length or two different types of linear density, in that case we can compare. So, in the term of work of rupture, say here gram force centimeter, we can say centinewton, say centimeter. This is the work of rupture, and to compare, so per unit gauge length. So, gauge length is one function. So, gauge length is centimeter per unit gauge length and per unit linear density, say tex. So, we divide by gauge length and divide by the tex of the yarn. So, effectively centimeter it is eliminated. So, effective practical unit of work of rupture of textile material we can express in terms of centinewton per tex, which is the unit of the tenacity. So, in that way also we can express. So, we can see here. So, this is the practical unit as I have mentioned. Here you can see this is gram force per denier, although the actual unit of work of rupture is gram force centimeter. So, effective unit gram per denier, gram per tex, centinewton per tex we can express. Now, our next parameter is work factor. So, we must remember one thing, that in work of rupture we are talking about load elongation curve, but in work factor we will deal with the stress strain curve. This difference we must remember. Okay. Now, this is the typical curve for stress strain behavior. Now, before that let me explain. This is a stress strain curve. Now, here strain, y axis is stress. So, if we see one material which follows Hooke's law, so the curve here is straight line from the origin. Now, if we want to measure the area under the stress strain curve, the shaded zone is area under the stress strain curve. So, and here one should remember work of factor deals about the entire stress strain curve, that means up to the breaking point, where in case of work of rupture we can measure the work of rupture at any point during the load elongation behavior, but here we talk about up to the breaking point. So, if we see here, this distance is the breaking strength. So, breaking stress, and here in x axis, towards x axis, this is the breaking strain. So, the point 0 A is the point where material breaks. Now, if we want to measure the area under the curve, so O A B C, so breaking strain will be O B and breaking strain is O C, this is C. So, O C is the breaking stress. Now, if we want to measure the area under the curve, so it will be, so area of the triangle OAB, that means half into breaking stress, that means OC multiplied by breaking strain OB. Okay. This is the value of the area under the curve. Now, work factor is not this area under the curve. The work factor by definition is the area under load, sorry, it is area under the stress strain curve, area under the stress strain curve divided by breaking stress multiplied by breaking. So, it is product of breaking stress and breaking strain. Now, if we try to replace, so area under the stress strain curve for a straight line stress strain behavior, that is Hooke's law, which follows the Hooke's law, half multiplied by OC multiplied by OB, and breaking stress here is the OC multiplied by breaking strain OB. So, if we, it will be ultimately half. So, it is a numerical value, and here a material which follows the Hooke's law, that is stress strain curve is a linear stress strain curve. In that case, the work factor is 0.5, that is the work factor. Now, let us say another material, take another material with say higher rigidity, and that also follows the Hooke's law, higher breaking stress, different breaking strain. In that case also, if we measure the work factor, in that case similarly it will again be 0.5. So, that means any material which follows the Hooke's law up to the breaking point, the work factor becomes 0.5. Now, so a material which, most of the material in fact does not follow the Hooke's law. So, material which goes through the bottom side of the straight line, here in that case the work factor will be less than 0.5, and which goes above, through above the line, straight line, work factor will be more than 0.5. You can see here. So, this is the curve. Here A material follows the Hooke's law, and B, the work factor for B material, the work factor will be more than 0.5, and for material C work factor is less than 0.5. So, by the value, by the parameter work factor, we can easily see the nature of the curve. So, work factor more than 0.5 means initially the material will exert or resist much, that means the initial modulus will be high if it is more than 0.5. If it is less than 0.5, that means initial modulus will be low. So, area under the curve. So, work factor we can see it describes the nature of the curve numerically. This is the most important point. So, we can describe the nature numerically. So, let us do some numerical. Here this is actually the numerical where work of rupture is required. So, we can see here for a typical yarn tensile test, the force is F in Newton and elongation E in centimeter, and they are related as F equal to 3 E square plus 2 E. This is the relationship. So, suppose this type of curve is there. Now, here we have to calculate the area under the curve. So, this function is given. So, what we have to do? We have to simply integrate. You can see. So, by integrating within the range of 0 to 3 centimeter, because yarn fails at 3 centimeter. So, work of rupture till breakage will be the integration from 0 to 3. So, by integrating this equation we get 3 E cube by 3 plus 2 E square by 2. So, e to the power 3 plus E square, it is from 0 to 3. Within that range, if we do it, we get the work of rupture 36 Newton centimeter, but here it is asked in Newton meter. So, it becomes 0.36 Newton meter. Similarly, next numerical is exactly similar to that, but here function is little bit changed and the breaking elongation is 5 centimeter. In earlier case it was 3 centimeter. So, we will have the similar solution. So, by integrating this equation, given equation, we get this value 2 E cube by 3 plus 3 E square by 2, and we have to integrate from 0 to 5 within that range. So, we get the value 1.21 Newton meter. So, next numerical also similar numerical. Here the function is given 4 F equal to 4 E to the power 3 and yarn fails at the elongation of 4 centimeter. So, we will take the range from 0 to 4 and first integrating this value function. So, we get integrating, we will get the value 4 E to the power 4 by 4. So, you can see, so this we are getting. So, 4 E cube, if we integrate, we will get 256 Newton centimeter and that is 2.56 Newton meter. So, we can go on doing this type of numerical. If we have different function, we can just simply integrate within that range. Now, our another numerical related to the work of rupture, it is during the tensile test of 2 yarns, we have 2 yarns we are testing, yarn 1 and yarn 2. Under the same test condition, the force in Newton and the elongation E in centimeter are related as this formula, F equal to 3 E square plus 2 E. Now, yarn 1 fails at 4 centimeter elongation and yarn 2 fails at 3 centimeter 8 centimeter elongation. So, suppose this is the condition and here elongation and this is load and this is yarn 1. So, here it is a 4 centimeter. Now, if we take the yarn 2, suppose this is yarn 2, it is 8 centimeter. Now, what it is asked that the additional energy, that is additional work of rupture required to break the yarn 2 as compared to yarn 2. So, this area, excess area is required. So, it is simple, we will just calculate the work of rupture of yarn 1 and yarn 2, then we will subtract. So, it is a simple one. So, 0.1 is the work, 0.8 is the work of rupture of yarn 1, 0.8 Newton meter, and yarn 2 is of 5.76 Newton meter. So, the effective additional energy required for yarn 2 is 4.96 Newton meter. So, 4.96 Newton meter is the answer. Now, the next numerical is to calculate the work factor of the yarn, where the stress strain behavior is given. So, yarn has a breaking strain of 3.5. Calculate the work factor of the yarn if yarn stress and strain are related as this one. So, yarn stress is sigma and strain is epsilon. So, sigma equal to 2 epsilon square. This is the relationship between stress strain, because in work factor we need, one thing is stress strain behavior, another thing it is up to the breaking point. So, breaking strain is given. So, we can calculate the breaking strain by replacing epsilon with 3.5. You can see here. So, breaking strain is given. So, breaking stress is 24.5 centinewton per centinewton takes. Okay. This is the breaking stress centinewton per takes, and then we are trying to calculate the area under the stress strain curve from within the range of 0 to 3.5 strain. So, we get the value of the area under the curve, it is a 28.58 centinewton per takes. Now, we have got the breaking strain, we have got the breaking stress and area under the curve. So, work factor will be nothing but 28.58 divided by breaking stress and breaking strain and breaking stress. So, if we get this value, we will get the work factor. Okay. So, work factor, so this is the work factor, the value comes out to be 0.33. So, work factor does not have any unit. Okay. And our next numerical is,
so by integrating this relationship, so sigma equal to 3 epsilon square. So, we get 3 epsilon cube by 3. So, 3 cancel out. So, it will be epsilon cube plus one constant, and which the constant will ultimately get cancelled out. Finally, it will be 1.5 cube. So, that is 3.375. So, effectively the work factor for yarn 1 will be 3.375 by 6.75 divided by 1.5. So, the value will be 0.33. That is area under the stress strain curve, breaking stress and breaking strain. So, this we can calculate. So area under the stress strain curve, breaking stress and breaking strain. So we can get the work factor of yarn 2. Now for yarn 1, the secant modulus, what is secant? The relationship is that sigma equal to 3 E square. This is the stress strain curve, and secant modulus at 0.1 stress. Secant modulus at 0.1 stress, that means stress at 0.1, so secant modulus at 0.1 strain, it was asked. So secant modulus at 0.1 strain, okay, and the stress at 0.1 strain by strain. So stress at 0.1 strain will be 3 multiplied by 0.1 square, that is strain is given, so it will be 0.3, and for yarn 2 the relationship is given 3 by 2 epsilon to the power half. So 3 by 2 epsilon to the power half. So if we want to calculate the breaking stress at the at the strain of breaking strain was given 1.5, so we can calculate the breaking stress 1.83 centinewton per tex using directly the relationship. Okay, this is the relationship, sigma 3 by 2 epsilon to the power half. Now area under the stress strain curve can be calculated in the same way, that is 0.0 to 1.5 strain. So if we try to solve 3 by 2 epsilon to the power half, that means if we integrate this, it will become 3 by 2 epsilon to the power 3 by 2 divided by 3 by 2. So this will get cancelled, plus constant, unknown constant, which will get cancelled out. So if we take the integration from 0 to breaking point, breaking strain 1.5, so it will become 1.5 to the power 3 by 2. So the area under the stress strain curve is 1.84. So breaking stress is known, breaking strain is known, and area under the stress strain curve is known. So work factor can be calculated. This work factor is 1.67, so which is more than 0.5. So we can calculate, if we know the work factor, we can see the nature of the curve will be that it will be initially the modulus will be very high. Okay, so it is actually from the nature of the curve we can at least predict whether it will be less than 0.5 or more than 0.5. And secant modulus at 0.1 strain, at the same way we can calculate the secant modulus at 0.1 strain. It's a 4.75. Now it's interesting. We can see in this curve the yarn 1 secant modulus was very low. This at lower strain, 0.1 strain. That means due to the nature of the carbon. So because at yarn 1, at lower strain level, the modulus is very low. Okay. Now solving the problem of tangent modulus. So tangent modulus, what was the tangent modulus asked? So secant modulus, tangent modulus at 0.1 strain, okay, and 0.2 strain. So tangent modulus, let us see at 0.1 strain. This is the differentiation of the point. So D, it will be D sigma D, D sigma D. So it is 3 E square. Okay. So it will, if we differentiate, 6E is the tangent modulus. So it is 0.6 at 0.1 strain. Okay. And at 0.2 strain for curve 1, 0.2 strain, it will become 1.2. So tangent modulus is increasing with the, for yarn 1, that means the stiffness is increasing with the strain for yarn 1. For yarn 2, you can see the tangent modulus at 0.1 strain is 2.37. We just simply differentiate and then we get the tangent modulus for 0.1 strain, and for 0.2 strain it is 1.68. So as the strain increases, the modulus decreases. Next numerical. A yarn has a breaking strain of 4. So it breaks at 4 times of strain. Calculate the work factor of the yarn if the yarn stress in centinewton takes and strain are related as 3 epsilon square plus 2 epsilon is the stress. So work factor is to be calculated. This we have already done, this type of numerical. So breaking strain is given. So breaking stress is calculated 56 centinewton per takes, and area under the stress strain curve is 80 centinewton per takes, and from there we can get the work factor. Work factor is 0.357. So it's less than 0.5. So from there we can actually guess the nature of the curve. So we'll stop here for today. So we'll continue with the tensile characteristics in the next class. Thank you.